welcome back to 6th grade science. Today we are going to continue our conversation about electricity. Specifically, we're in electricity part 3. Let's start with resistance. What is resistance? In the case of electricity, it is opposition. Specifically, it's opposition to the flow of electric charges in an electric current traveling through matter. So as electrons are flowing through a current, they're bouncing around and hitting the matter that they're traveling through. And by hitting the matter, I mean they're hitting the atoms of matter, of whatever matter type that they're traveling through. This reduces the total amount of electrical energy that's transferred. This is because electrical energy is being absorbed by the atoms that they run into. Remember conduction from our previous discussions? When the electrical current runs into the atoms of whatever material they're passing through, it is giving off a little bit of its energy through conduction. So remember, energy cannot be created or destroyed. A little bit of the electrical current is being transferred into a different type of energy, such as heat or light. I keep referencing different SI units as we go through, and the SI unit for resistance is the ohm, OHM. No matter what type of material the electric current is passing through, they all have varying levels of resistance. How much resistance depends on a few different factors. These factors include the width, the length, and the temperature of the material that they're traveling through. Items that are electrical conductors have less resistance, and items that are electrical insulators have more resistance. The wider the wire, the less resistance it has, and the narrower the wire, the more resistance it has. Think of this like a roadway. When you have a very wide road, like the ones that have 3 or 4 different lanes, you can fit more vehicles there, or you can go around things easier if there's less traffic. When you get down to 2 lanes or even 1 lane, the roadway itself narrows a lot, so your car only has so many places it can go. So the wider lanes offer more spaces for your vehicle to travel without hopefully running into anything. And the narrow lanes give you very specific spots that your car is able to go. It's the same way with electrons traveling through wires. The shorter the wire length, the less resistance there is. And the longer the wire length, the more resistance there is. When the energy only has to travel a little bit, it's going to bump into a lot less things than it would be over a longer period. The cooler the wire, the less resistant it is, and the warmer the wire, the more resistant it is. Resistance can be a good thing or a bad thing. It just depends on what goal you are trying to achieve. When you're setting up your circuitry, if you are just trying to transmit electricity from point A to point B, resistance is a bad thing because the amount of energy you can get from point A to point B will be less when you have more resistance. If your goal is to produce heat or light, then resistance is a good thing, because that's how electrical energy is used to create light or to create heat for different things, like an electric heater or an electric stove. In each of these instances, resistance is good because it's accomplishing the goal that you want it to. Moving away from resistance, we're going to get into conductors and insulators. Now, if you remember from a few weeks ago, we talked about conductors and insulators with something else. Anyone remember what it is? This background will give you a hint. Yes, it's thermal energy. So remember, with thermal energy, conductors were ones that transmitted thermal energy well, and thermal insulators are ones that did a better job at holding in thermal energy or holding in heat. It's a similar idea with electrical conductors and electrical insulators. Remember that electrical energy is transmitted by electrons moving through a current. Electric current needs matter to travel through because it can't travel through empty space, but matter resists the flow of electric current. Different types of materials offer different levels of resistance. You have those that are very good at allowing electricity to flow through, and you have those that are not very good at allowing electricity to flow through. This brings us to our discussion about conductors and insulators. Electric conductors are any type of material that have low resistance to electric current. This means that electricity flows easily through them. Many metals are good examples of electric conductors, and the reason is because the outer electron in the metal atoms is looser and free to move. Another good example of an electric conductor is water, but pure water is not good at conducting electricity. It has to have some kind of impurity in it, whether that's iron particles or some other type of particles in it, but pure water is not good at conducting electricity. Water like you'd get from the tap or bottled water or anything like that is good at conducting electricity because of the impurities in it. Electric insulators, on the other hand, are any type of material that have a high resistance to electric current. Non-metallic solids are typically what people think of when they think of good insulators. That's your woods, plastics, and rubber. The reason that they're good insulators is because their atoms hold tightly onto their electrons, so electric current can't flow freely. Another good example of an electric insulator is dry air. You might remember from the video that I talked about lightning that electrical energy doesn't travel well over air, and I mentioned dry air specifically, because without the water molecules in it, it doesn't act as a good conductor, rather it's a good insulator, so electric current doesn't flow freely through it. Now, if you've ever seen a wire, or if you look behind me right now where there's some wires, you notice that a lot of them have a plastic coating around it and then the metal wire on the inside. This is creating the path of least resistance, because you have the plastic, which is a good electric insulator, and you have the metal wire, which is a good electric conductor. Whenever given the opportunity to travel through something, electric current always picks the path of least resistance. So because it can flow better through the metal, it will flow through the metal and it will ignore the plastic. Or ignore, but it doesn't actively try to flow through the plastic, instead it flows through the metal, because it's easier to flow through the metal than it is the plastic. Moving away from conductors and insulators, let's talk about Ohm's law. If you remember from the beginning of this video when we were talking about resistance, we talked about ohm as the SI unit of resistance. This law is used to describe the relationship between electric current, voltage, and resistance. The formula for this, which would be a good idea for you to know and to recognize as Ohm's law, is electric current equals voltage over resistance. Another way to write this is I equals V over R. I know that before we talked about the SI unit for current being ampere, but in science, sometimes things are a little confusing, and so we're going to represent the word current with the letter I, a capital I. So current equals voltage over resistance, or I equals V over R. This equation can be used to calculate a few different things. If we know the voltage and the resistance, we can use it to calculate the electric current. If we know the electric current and the resistance, we can use it to calculate the voltage. And if we know the electric current and the voltage, we can use it to calculate the resistance. Up next, we're going to talk about electric circuits. An electric circuit is a closed loop that electricity can flow through, or that an electric current can flow through. The amount of electric current in a circuit is dependent on a couple different things. Number one, how many electrical devices are connected to the circuit? Number two, what is the power level of those devices that are plugged into the circuit? Most home circuits generally have an upper safety limit of 20 to 30 amperes. What makes up an electric circuit? All of them have at least two parts. You have your voltage source and a conductor. More often than not though, your electric circuits aren't going to be made up of just these two items. Instead, there are other components to it too. These other components include light bulbs and switches, as well as other things. But in a simple circuit, like the one here, you have your voltage source, which is the source of electricity. You have the switch to turn the lights on and off, or to open and close the circuit. You have the light, and then you have your conductor, and in this case the conductor is the wire. Your wire connects the power source to the light bulb. Partway through you have the switch, so when the switch is in the off position, the circuit and the light that it's connected to are off because it opens the circuit, so it's not connecting. Then when the switch is on, the light is on, and that's because the circuit's closed, so electricity travels through to get to the light. Circuit diagrams, like this one, are drawing representations of electric circuits. These are used with blueprints and design. These circuit diagrams use standard symbols to represent different components in the diagram itself. There are two different kinds of circuits. The first one is the series circuit. A series circuit is a circuit system that consists of just one loop. If that loop is interrupted at any point during the series circuit, electricity can't flow from point A to point B, so whatever's connected to it doesn't work. In the example I gave earlier with the light switch, when the switch is in the off position, the circuit is open and electricity can't flow where it needs to, which is why the light's off. When you switch that switch back on to the on position, then the circuit becomes closed and electricity can flow where it needs to. The other type of electric circuit is the parallel circuit. This consists of two or more loops instead of the one that you find in the series circuit. If one loop is interrupted in a parallel circuit, current can still flow to the other loops. A good example of an item that has both a series circuit and a parallel circuit is Christmas lights. When you have a bulb go out in Christmas lights, part of the string of lights stops working. That part is on a series circuit. So when one light bulb stops working, every other one in that circuit stops working because there's no current flowing through it. But at the other part of the string, the lights are still working. That's because it's split into series circuit, which is the string of lights or the section of string of lights that is out when one is out. And then you have the parallel circuits, which allows current to continue flowing to the other lights on the string. So the part that is not working is part of a series circuit, and the part that is working is part of the parallel circuit, all on the same string of lights. That's all I have for you today. So as always, if you have any questions, please remember to reach out to your teacher, whether that's Miss Cameron or myself. Bye.